Is my pointer visible and the slides? Cool. Okay. Uh, so, good evening, everyone. So, after a long break, we came again on this session. So, I hope you have gone through the some of the materials that I have shared in the email. Yeah. Anyone? So, let's get started. Today we will just understand some basic concepts of signal processing, which will be useful in many domains, not just neuroscience. So, how many of you here have done or have read some signal processing right now in the class? Whoever is there, can I see some hands? Okay, two, three. Okay, good. Okay, seems like some of you are aware of this and have done some course or have seen through the signal processing. So, today will be mostly basics because we want to get everyone in the session on the same baseline. So, we'll just try to see like what are the different types of signals, what are the different parameters that can define a signal. Okay. So, yeah, you can lower your hands. Yeah, cool. So, so in the last class from neuroinformatics session, we have discussed just a visual representation of how a Fourier transform looks like, or how to visualize the frequency. Give me a second. Yeah. Okay. So, Atharva also joined just now. Okay. So, Atharva, can you help me if anyone asks any question or yeah. We can't hear you, but it's okay, fine. So, okay. So, this part is visible, right? Yes. So, can anyone give some examples of what a signal means, or what are different types of signals that we see in our day-to-day lives? Oh, sorry, I can't. Okay, okay, 1 second. Yeah, yeah.
I think here.
Okay, so Deepak, can you hear me now?
Yeah, yeah. My system was on mute. Yeah, yeah, sure. Now I can hear.
Oh, okay. So I was telling, can you make me a co-host?
Yeah, yeah. I made you co-host.
And then I can.
Ouch. Yeah.
I thought my mic was not working.
Okay. Yeah, yeah. So, so here are some examples of signals in real world that we see in our day-to-day lives. For example, this first thing that I'm showing here is a audio waveform. This is a typical audio waveform, how it looks when you talk and try to record on your microphone and plot the voltages. So this is a typical audio waveform. And then for example, the stock prices are also a set of numbers has time progresses, right? Like for example, in a day, what is the price of a stock? So if you plot across days, you get a type of signal of this sort. And this is also type of signal that we see in our day-to-day lives. And there are this biopotential signals that we see, like uh, for example, whatever the main part of this course, the EEG and this biomedical signals such as ECG, etc. So these are you can easily visualize that as the time progresses, you are plotting the value of a particular thing, such as microphone's voltage, or a stock's price, or the heartbeat, some signal detected due to the heartbeat, or due to brain activity. So these are one kind of signals. These are usually called one-dimensional signals. And we have uh, so these are signals in time, like as time progresses, how a certain value changes. But there are also signals in space. Can anyone give an example of what a signal in space is, or if any guess?
It can be like a temperature in a room.
Temperature in a room, yes, correct. So you can have a heat map of a temperature in different parts of a room. So that is a kind of like Vinod told, it's a kind of image. Like you have a xy coordinate of a location, and at that location you have particular value. So even images can be considered as a two-dimensional signals. So for example, this is a MRI image of a brain. So here at any given x and y value, you have particular contrast, or particular shade of this black and white. So this value corresponds to a similar value in time, but this is in space, the x and y coordinates. And there are also three-dimensional signals. It's nothing but if you stack this two-dimensional signals across time, you get a video. So these are all typical signals that we deal with in our day-to-day lives. Okay.
There can even be four-dimensional signals.
For example,
means 3D space and time. X, Y, Z coordinates and time.
Oh, that way, yes. They can be four-dimensional also. So, yeah. So there are like multi-dimensional signals are also possible. You can form a like multi-feature vector and how it changes across time. You can also, like, it depends on how you visualize, but yeah, these are just few examples of what signals we deal with in our day-to-day lives. Yeah. So just wanted to mention about different types of signals in our classified according to how the time and the values are present. So there are mainly two types of signals based on how we sample the time. One is continuous time. That is, the time is very continuous, it just goes on. There is no discrete values that it takes, and there is a discrete time signal which only takes particular values like 1, 2, 3, 4. For example, if you take a stock market signal here on the x-axis, these are discrete values. It is each point on x-axis corresponds to a particular day. So these are discrete times. Whereas if you see an audio signal, it is like as the time progresses continuously, how your voice changes, so, or the microphone's voltage changes. So this is a type of continuous time axis, and this is a type of discrete time axis. Is this part clear? What is discrete time and continuous time? Okay. So further, this discrete and continuous time signals are divided based on their amplitude also. One is called continuous amplitude, or if I mention here as continuous signal. So yeah. So how does a continuous signal look like? Let's take some example of a signal here. So this is typically a amplitude modulation. If you have heard of AM wave or AM radio, so those signals looks like this. As the time progresses, how the amplitudes change. You see a slow envelope going on top and high frequency oscillations inside the envelope. So here we see that the time is very continuous. So like as the time progresses, the amplitude also takes continuous values from, for example, here minus 1.5 to 1.5. So basically what I mean is it's not taking any discrete values, like not just 1.5 or 1. It is taking a continuous set of values. So this is example of a continuous time continuous amplitude signal. Next, there is also continuous time discrete signal. So this is little tricky because we don't usually see continuous time discrete amplitude signal. So this happens when in a computer, right? We have, like, computer cannot store infinite values. It actually quantizes because it's a representation in ones and zeros, and this ones and zeros, based on how big is the storage, you can only take those discrete values. So basically what happens is this kinds of a signal, let's say a sinusoid signal like this. If you see here, there is a sinusoid in the, can you see the dotted line behind the blue trace? Yeah. So this is the one behind the sinusoid is a continuous signal, but the computer can't store all the values, right? Because it has a finite storage space, and based on how the number is represented in and the number of bits, it takes on discrete values. So a same thing in a computer, it can be quantized. So basically it can take only particular levels of the signal. So approximately it approximates the signal and makes it flat there, and as the time progresses it plots. So this is an example of a continuous time discrete amplitude signal. Discrete amplitude because it can take only certain quanta of levels and not continuous levels. I hope this signal is clear. What is meant by this?
Deepak, good question.
Yeah, sure.
So, just curious, at what rate does this quantization happens in our modern computers? Because it should be much greater than the rate at which we sample the data, right?
Correct. So it actually depends on the clock speed, and so basically computers have a clock, right? It keeps updating the data as they come. So, and are you talking about the levels of this? How are these levels?
Yeah, these look pretty big actually, right?
Yes. So
And here sort of these the quantization rate, so to speak, is some 10 millisecond or something.
yeah, you can see a small, yeah, correct. So it depends on the clock speed. This is just an example.
But this is not in time tempo. This quantization happens in bits, right?
Correct.
So if you are storing in 32 bits, then you can store 2 to the power 32 integers in that. And if your readings are integers only, then
yeah, so basically
like
if it's a 24-bit computer,
that defines basically the step size that you can take. So how many integers? Like let's say you are storing 100 numbers from 0 to 100 in 2 to the power 32 integers, then your resolution is 100 by 2 to the power 32. That's the step size that you can take minimum. Did you get it?
So otherwise, it directly doesn't affect the sort of the quantization rate in time that we are talking about here.
Is it different? Then no, it is. This is in time, but even if it is like varying in two, let's say step, not a continuous wave function. What is the minimum step size that you can detect using a computer?
Yeah, basically this otherwise talking about these levels, which are like, you can see only like 0.25 resolution, right? So yeah, so this is based on how a computer represents a number. So like Atharva mentioned, if it is 32-bit, the values can be from 0 to 2 power 32 levels. It can't take anything like continuous. So that is the main point here, that is, time is continuous and as the time progresses, what are the values. So this happens during quantization in you know in computers, or yeah. So basically you can't represent a number exactly, you have to quantize it to some level, and those are like discrete levels. So this is an example of continuous time discrete amplitude signal. Okay, and then there is also discrete time continuous signal. Okay, so can anyone tell an example of a discrete time continuous signal from whatever examples I have given earlier? Discrete time continuous amplitude. So the values
Stock
on
prices was like that.
yes, exactly. Yeah, Vinod was right. So as Vinod told, in the case of stock prices, for example, this is an example simulation of a stock price as the days progress. So on x-axis you see days which are discrete, like you don't have continuous time values here. You only have for a particular day, day 1, day 2, and so on. So these are discrete days, and on y-axis the prices can be continuous. It can take any price on a given particular day. So this is an example of a discrete time continuous amplitude signal. Okay, and also there is a
Doesn't it depend on the level of resolution? The price of stocks vary till 2 decimal places. So after the third decimal again can be discrete at that level. If you see, uh,
I see.
means it depends on the level of
Correct.
resolution you want
Level.
to
Yeah,
look at.
yeah.
Uh,
Correct. So why are these types of signals important? Like it depends on the resolution, but if it takes discrete values, like in this case it is 0.25, and you're saying in this case it will be up to 2 decimal points or 3.
yeah, means whatever. It also has every signal has that limit of precision
Yeah,
that it can,
correct. So
unless it is a
yeah, in an ideal
math
case,
function.
like if you're not representing like if you want to represent exact values, for example, then like stock price can take a continuous value because it's money, right? So it's a price kind of thing. So if you represent in a system, then it takes a quanta of values because a system has a certain level of precision. It can't represent like more than few decimal places based on the type of system you're using. So yeah, so yeah, these are ideal scenarios. In real cases, in when you represent a signal in your system, it's always quantized to certain level, as Atharva told. But if you think of it as a like actual price or actual value, then this can be a discrete time continuous amplitude signal. uh, and also there is a discrete time discrete amplitude, both in amplitude and time it is discrete. So usually these are uh, you know for example, if you are showing a bits or a Morse code sent over a transmission line at certain times, then you see like at this point of time you have a 0 value and next this value. So this is a discrete time discrete amplitude signal, and you can have sometimes multiple levels also. You can, instead of representing only 2 levels, you can have a 4 levels, like you can only have 4 numbers here. So that becomes a discrete time discrete amplitude signal, and time is exactly sampled at different periodically sampled at equal intervals here. So there are some modern techniques which can sample at non-uniform sampling rate also. There you don't see a uniform time there. So that are another type of signals. So why are this like we discussed this, but why are this important? Based on the type of signal it is, based on whether it is continuous in time or continuous in amplitude, the way we extract frequency information changes slightly, and the way we analyze or see like what kind of frequencies are there in different types of signals also changes. It's not just one kind of a Fourier transform. So every type of signal has a different type of Fourier transform that we perform. So that thing will come in the next class, but right now just an introduction to what different types of signals are. Any doubts until this point?
Deepak, that binary signal that you showed at the last, where do we encounter them? Like where is it recorded?
So this is exactly how your computer represents any signal. So all any type of signal that your computer represents is always a discrete time discrete amplitude because it does sampling, because it has a certain clock speed, right? So it can't have a continue like a physical signal like a noise or compressions and rate fractions in the air. If you actually see, they're continuous, but if you actually store them in a computer, it is always in terms of this. And this is 0 1, but you can show multiple levels also here. So
This can be considered as a spike signal, right? Means when you measure neuron activity and you
yes,
already done like identified spikes there,
correct,
then whenever spikes occur, you call it 1,
yes,
and when they didn't occur, you call it 0.
yeah,
So that can be considered as
yeah, uh, yeah, correct. So wherever a spike occurs in a neuron, you can mark it as 1, else 0, and you can do that periodically. And when you do that, you can plot this kind of a thing. And actually, like in the maybe in the future session, you will see how spiking data can be represented. It's called a raster plot, where you can represent this kind of thing for multiple neurons, and it forms a raster plot where you can see how a population of neurons spikes, etc. So that is one example of discrete time discrete amplitude. But usually any signal you store in a computer usually takes this form, because it takes a discrete in time as well as discrete levels on amplitude as well. So it's a mixture of this discrete time and this quantization levels that you see here. So this is how your computer represents. Okay, any other doubts? So if I plot firing rate in different time zones, yes. So yes, correct. So Ishita mentioned, if I plot firing rate in different time bands, that will be a discrete time continuous signal. So basically you count number of spikes in particular set of time points. So that way, like you can see, like if you take this window has 3 samples, you will see the value has 3, but at different times it is only one, like you'll get a signal like 1 1 3 going on, mm, but it becomes a discrete time and still discrete amplitude itself, because amplitude can take only this integers. It doesn't take like you can't get 1.1 or 1.5 spikes. Is it clear?
actually we can get 1.5 spikes, but um, like it will be depend. The rate can be non-integer, but it will depend on the window size. So
Acha,
then window size. Let's say if the window size is 5 seconds, you divide the number of spikes by 5. So it will always be like 0. 0.1, 0.2 or something like that. So it will be discrete because
okay, if you're
it will
dividing
depend on
by the time,
yeah,
yes.
yeah, it will depend on the remainder that
Yeah,
is
yeah.
left
Instead of samples,
with
if you
you.
take, yeah, correct.
So the remainder can be 0.2,
Mm,
0.4 or
yeah,
uh, 0.6, 0.8 and 1. So
correct.
that again becomes discrete.
Hmm.
And the time bins are when you're taking firing rate in the time bin, you assign it to the discrete time bin, right? Even if you have an analog computer measuring it, you have the discrete
Correct,
time bin
correct. Yes.
assigned to that, so it is automatically a
Hmm. Correct, correct.
discrete
Yes.
time, discrete signal.
Hmm. Yeah. So, hmm. Cool. Okay. So, if it can read audio, but yeah. Hmm. So last time we have seen a picture of this sort. Give me a minute. So uh, do you remember this kind of a representation that we showed last time? So so here we are going to get into a bit of Euler's representation, because this will be useful in understanding the Fourier equations. So let's do with this code here. So first we'll understand what is a Euler's representation. So for now you remember there is only like one sinusoid signal. I wanted to show some real-time thing, but I think because my microphone is being shared at two places, it's not able to read it. Yeah, anyway, fine. We'll see later. So, is anyone aware of this Euler's representation or Euler's representation? It is okay. How many? Yeah, okay. And how many of you are aware of sinusoid signals? Okay. Yeah. I think many people know how a sinusoid looks like. Oh, one is. Okay. So, 1 second. It's gone here. Okay, we'll see here itself. Yeah. So, here there is a code here. Yes, sinusoid signal is represented by a sine function. Correct. So, what we will do here is let's run this. I think it is already and yeah, fine. So first we draw like e power I theta. Here it's e is the exponent, e is the base, and exponent is the I theta. It's an imaginary number. So what does it mean is it's nothing but sum of cos plus right now you don't worry about what is I. It just rotate anything by 90 degrees on a polar plane like this on a circle. So if you want to rotate this number, if you want to bring this number to this part, what you do is you multiply by I, the imaginary number, then it comes here. So basically you're multiplying, you're adding cos to a imaginary part with multiplied to a sine value of theta. So theta is nothing but the angle. For example, this is at 0 right now. So yeah, this is at 0, and as you increase theta, it goes on the circle like this. As the theta increases. So this theta, if you start rotating it, start increasing theta, if theta is a variable as time progresses, then this starts rotating around this unit circle. What I mean by unit circle is a circle with unit radius, and as theta increase, this point starts moving ahead as it increases. So now for this we can also control the rate at which it rotates around the circle. So that exactly defines the frequency of a signal. Okay, so this is just a code for plotting these things. So we are just getting some points in two-dimensional, ranging from 0 to 2 pi. 2 pi will be the circumference of the unit circle. So in that you are getting 300 points, and then making this circle here, as you see, the blue one, and then you are changing the vector according to theta. So as theta takes on different values, how this change, and we start moving continuously as theta increases, what happens. So let me play this. So you can see, right, it is rotating at a particular frequency. The speed at which it rotates around this circumference of the unit circle, that defines the frequency. And when you plot, so let me stop for a moment. Yeah, so you can see this pink line and the green line, right? So this is called the y-axis here is called imaginary axis. Any value here will be like some j times, we'll discuss what is j and all in a bit, but any value on this y-axis is called imaginary axis, and any value on this x-axis is called real axis. So these are all real numbers, and these are all on this axis you find all the imaginary numbers. So now what you're plotting here is the height of this. So how, like the height of this green and the height of this purple, you're plotting on a one-dimensional plane. So then what you see is, you see a nice sinusoid moving this way. So as you saw, it just like starts moving here. So you see here when you play, so here the green color at this point goes to 0, like the height of this green is 0 at this point, and as it starts rotating it increases and then comes back to 0, and then again it increases. So that's what you see here. This is a cos curve and this is a sine curve. So any sinusoid can also be represented in this format, which is called Euler's representation. So it just shows different values in an polar plane, and polar plane can be represented by real and imaginary axis. And if you want to rotate this, you represented this by e power I theta, and as you change theta, it rotates around the circle. So is this equation clear, or any specific doubts here, if anyone is not aware of this representation? Okay.
Deepak, if if we take the form e to the I theta, then I think we can only represent sort of this combination of two sort of cosines and sines, two orthogonal signals. But if we sort of have to represent a pure sinusoid, let's say, which kind of doesn't mix up with anything, any cosines or other frequency terms, then we need to use some combination of different e to the I theta 1, theta 2, etc., right?
Correct. So yeah, that exactly is what we do in a Fourier transform or Fourier series. Okay, so Ishita is asking what quantifies the rate of rotation. So here, for example, I'll just stop this a bit. Yeah. So here this theta actually represents the angle from this horizontal, right? And as you increase theta, it varies. But if you start increasing at the constant rate, so if you add a time term to this, like if you say theta is a function of time, theta is equal to 2 pi some constant times t, that constant uh, represents the rate of the rotation here. So here theta, in this theta variable I have put that in the code, if you see here clearly. So there is a frequency term here, and what am I doing here is angle, that is the theta is nothing but like it is dependent on frame, because here frame is like a time. So some constant here 2 pi because we need a circular space here. So and this frequency, so this term, the rate at which you are changing the angle, if that theta is a function of time, then there is a constant that multiplies with that time value, so that determines the rate of rotation, and that is what is called frequency of a signal. Or yeah, is it clear, Ishita? Yeah. You generally write theta is equal to 2 pi ft, and f represents the frequency. And as time progresses, you can fix the f is fixed, and theta is a function of time, so that defines how fast it rotates. Okay. So as Vinod was saying, so here in the last session, sorry, yes. So as I show you here, so as it rotates at one particular rate, you see one frequency of oscillation. It's a constant, like it cycles in a constant rate. But if I increase the frequency as it goes faster, within this time you see many cycles coming up. So that defines the frequency of this. And usually what we do is the x here is theta as I shown in the code here. So this will be the imaginary and this is the real axis. And if you want to rotate this vector, you represented this by e power ix. So any point can be represented either in xy coordinates like this, or you can represent on an arc rotating using this e power I. So why this is important is with this kind of a notation, we can get oscillatory patterns of this sort. So, and if you increase the f, the rate also increases here, how fast it rotates. So basically you are differentiating it by time. If you do dx by dt, you get 2 pi f, and that defines the angular velocity or frequency of this. So that's the idea. So now in the last session we have seen that for example, we saw this signal, like this green colored trace here is sum of two signals, that is one going at 2 hertz and one going at 3 hertz. So this signal can be represented as sum of these two signals. Similarly, for example, if you take a square wave like this, the dotted line as you see here, can you see a dotted line here behind the curve? So this signal can be represented as sum of many sinusoids. So similar to the previous one, we saw a very simple signal, just sum of two. And if you take the square wave, and if you start adding as many sinusoids as possible, you start to approximate to the square wave here behind. So similar to the square wave, any signal can be represented as sum of sinusoids and sum of sines and cosines, not just sines, because sinusoids are both sine and cosine, just a phase difference. So that is another parameter called phase for any signal. So if you write this in terms of mathematical equation, what do you get? A square wave across time. You can write as sum of each of this. Like you can add this to this, and so on and so forth. So for this square signals, as we add more and more sinusoids, it gets more closer to the square wave, and at infinite point it becomes exactly square wave, which is practically not possible. So we stop at some point after few, like once we are satisfied with it approximated enough. So any wave can be represented as sum of sines and cosines. Is this clear? If this is clear, only we can understand Fourier transform. If you have any doubts, even if it is basic, please ask it here.
I mean, it's very. You said that any signal can be represented as sum of sines and cosines. So, means I know the cosines are also sine
Yeah.
90 minus theta, but like only the sine terms in that Euler transformation, the real part,
Correct.
can represent a one-dimensional signal, right? Means you don't need the imaginary
Yeah,
part there.
correct. So yeah, correct. So there are other type of signal called even and odd. So someone is saying, 1 second. There's a question in the chat.
I will read that out if you want.
Uh, so you're saying like why do we need cosine and Euler's representation instead of just this? You can
Yeah,
just represent it as sine wave.
means it's important for understanding, but is it important? Is like does it also plays a role somewhere in the transformation itself? Can you
Yeah,
tell me?
so I'll show in a bit, right? So here I am showing only sine, one type of a wave here, but in general, like for example, any signal can be represented of this sort, where there is some constant which decides how high or low is the signal from zero, and there is sum of sines and cosines here, right? So what it says is how much. So it's not always that all the signals will have a zero phase. They might have some phase shifts, and that can be represented like there might be some 90 degrees phase shift which becomes a
I
cosine.
see.
So you generally approximate any signal of this sort. So that actually depends on whether a signal is even and odd. And okay, I haven't thought what is a even and odd signal, but for now you just take it that there are two types of signals. One is even and odd signal. So even signal only sine is enough, but if it's an odd signal, you need a cosine term or the imaginary term there. So
I see.
yeah, so you need both sines and cosines to represent a signal, and both sine and cosine, although they have phase difference, they have the same frequency. If you see here, fi and fi, so some constant times cos plus some constant times sine. So like that you have multiple sines and cosines. So now what this says is this equation. This is called a Fourier series representation. This AI says this much weight, like this much amount of this particular sinusoid uh, is a part of the signal, and so on and so forth. So now what does this AI and BI mean is nothing but what is the content of the signal for this particular frequency Fi. So this Fi is of like this much, this much component is there, like this much quantity of this particular frequency sine, and this much of this particular frequency cosine is there, and they're of same frequency. So now for finding a power of a signal at a particular frequency, you just need these terms. You must know what is AI and BI together. So is it clear? Yeah. So I'll show more clearly in maybe next class, but we can derive from here. So this is a main equation that from the definition that any signal can be represented as sum of sines and cosines, how can we get the power of each frequency, or how much of in a given signal, how much of this frequency is present. So basically, if you can represent, if you can somehow, there is a way to find these coefficients, this AI and BIs, and there is a method to combine both of them together. That is why we use Euler's representation, where we can use Euler's representation to combine both AI and BI together, because this is of same frequency, this is of same frequency, just the phase is different. So that is where the Euler's representation comes into picture. So yeah, what's the
So Deepak,
yeah, Vinod?
so, yeah. So I guess once we get to Euler's representation, then these constants might be some combination of these AI and BI, and it might turn complex. But here, AIs and BIs should be
Correct.
real, right? If the
It is real.
signal
Yeah,
is
yeah.
real.
It is just, yeah, it is just one-dimensional signals. Just they
Yeah,
have
we are just we are just adding up real numbers to get a real number f.
correct. Yes, yes, exactly. So that Euler's representation comes little later when we try to combine this AI and BI. So it's a form of a hack to find like to basically find this frequency content of like how much amount of this particular Fi signal is available, and Fi can be ranging from 0 to, it can go to until infinity here. So it can be multiple frequencies, like as we see here. So although I'm showing only few here, as you keep increasing frequency and multiplying, you get more better approximation of a signal. So in this particular case, the BIs become 0. So
Important thing to note here is that sine omega t and and cos omega t are two signal with frequency omega. Let's say it's actually omega by 2 pi, but
correct.
Then a sine omega t plus b cos omega t will also have that frequency of omega. Means
correct.
if you just take linear sum of them, then the frequency will not change, only the value will change. Like the signal will be periodic again with frequency omega, right?
Yes, it will be of same period and the same frequency, correct.
Okay, only the waveform will change.
Yeah,
Okay.
this is the waveform. Waveform is little off. Like if you see cos, yeah.
I made that figure just now.
Yeah,
Okay.
as you see here also, like if I show you this this thing, so this is sine and cosine from this Euler's part. You see they go like in a like off phase, and the phase is exactly like 90 degrees. So when this becomes 0, this becomes 1, and so on. So when this is minimum, this will be the maximum, and when this is maximum, the green one will be the minimum. So yeah. So the proof of Fourier transform and how to get it from Fourier series. So basically Fourier transform, how we do is we try to find this coefficients. So we'll discuss that in the next class. Okay. So this is the Euler's representation, and I hope this part is clear. It's not too confusing. It will become more clear when I start seeing how to get frequency in a signal, when I give a proof of how to find this AIs and how to relate this with the Euler's representation. So if you had gone through the material that I shared, so basically what we are saying is if a signal is there and you want to find this component, so basically if I try to find these AIs and BIs, how do you get the end equation? I'm not dealing with the steps, I'll like show that in the next class. So this capital X of k is nothing but how much of this, it's like AI, instead of AI comma BI, you are representing the whole thing in terms of xk. AI BI together you are showing in terms of xk, and there are some signal samples. What you do is that signal you rotate around that unit circle and the frequency at which you spin, at a particular frequency you spin, and the points you average, so that will give you the power of that particular frequency. So we'll see how this comes out. So basically this is the main equation of how you can find a frequency content of a signal, a given frequency, or like what is the amount of a given frequency contained in that signal. So yeah, one second. Is it recording? Just give me a moment. I will try to. Hello?
Hello? Hello?
Wait. Okay. So I will try to show a real-time reading of audio, so that we can use that as a tool for uh, showing many operations on the signal. I'm just trying. I'll not be able to hear you guys. I'm just trying if I can. Okay. 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 So you can see this plot, right? Okay, so I'll just change some of the axis here. So yeah, so this is a code which actually reads your voice from the microphone and then plots it as a waveform. So this we can use for our next classes as a simulated data for doing spectral analysis, the Fourier transforms, or any other operations. So yeah. So what is happening is we are actually importing a library called sound device, which connects your microphone to the Python script here, and it can start using this. It can start listening to your microphone, and these are some standard libraries for plotting and doing some array operations. Then we define the sampling rate. Right now you don't have to worry. It is based on like what we have discussed previously, that your computer needs to sample signals. So it is sampling at 44.1 kilohertz, like this many samples per second, like your voice is sampled at that much, so at that rate. And we are defining the chunk here. So in real time what we do is we read a part of your voice and store it in a small buffer. It stays for some time, and then we can plot it every 2 seconds here basically. Every this many samples per frame here, just to keep updating. And this is a code which creates a plot, and it does a callback function where it calls itself, and uh, you will keep updating the plot here, and in real time this is the real time thing. You can explore this code and try to do some operations that we deal in the next class. So what happened to this? Wait. Okay, let me do again.
Is your microphone available?
Yeah, somehow it is being shared with the Google Meets and it is causing some problem, but I stopped my microphone there.
Yeah.
Yeah, just give me a minute. I'll just have to run again. Yeah. So as you see here, as I speak, just a moment, it will come. So as I speak, you can see after some time it changes. The waveform changes according to how I speak here. So
Whistle.
yeah. You want to whistle? You can whistle. I think it is hearing to you also. You can.
Oh, even my voice is going there?
Yeah. Yeah. So this is doing every 2 seconds. So now we can use this and do some operations which I will be dealing in the next class. So I will also show like for the same signal how we can plot in real time some spectrums and draw some nice patterns in that spectrograms or spectrum. So I'll share this code so that you can try with on your end and see like uh, how they vary. You can also do some, you can sing some notes and see, you can see a constant oscillations coming up like this. So yeah, so I can actually show the other thing also, but yeah, fine. So I think for today's class that's it. If you have any particular doubts or if you didn't understand the Euler representation, we can go through it.
So in this sort of demo, it's the limitation of that collecting for 2 seconds and displaying. Is it because of the sound device library or something?
Oh, you can change the, if I increase the samples, you will get more samples. If I do like 409, oh, you're saying the number.
Yeah, is it possible to sort of show it every 500 milliseconds or every 100 milliseconds?
Yeah, it is possible to show even for short periods. So, but if you're doing a Fourier transform on it, it needs some time. So, but right now we are just showing the raw samples. It is just to plot. If I do like some 1000 samples here, it will show for by 1000. It will show for like 44.1 seconds. So this is samples. Based on samples we put, it's not exactly 2 seconds. Okay, I think this is interacting with that. Yeah. So even your voice can be represented as like this sum of sinusoids and cosine. So and then we can do a Fourier transform to find these coefficients ai, bi, and find which frequency has more energy. Or you can also decode which note you are playing based on this. So I'll show some music demo in the next class where we can play some music and see how the spectrum changes and if we can decode what note a person is playing. Or sort, yeah. So
It's a potential use cases in our analysis. Is something
Yeah.
that
So
we should discuss. So one thing I say that my part, like in the photometry that I taught, the filtering, uh, in when we took take samples and we applied high pass and low pass filters to remove the noise. So you can design filters many ways. We also saw median filter, right? Means which took the median value of the 5 samples. So that does not involve any change from time domain to frequency domain. But there are ways in which we can do this time domain to frequency domain and uh, remove specific frequencies, like 50 hertz, for example, is a common noise in India, 60 is in US. So
correct.
that kind of signal processing require this Fourier analysis, and since mathematical foundation is there.
Yes.
Uh, Other is in like signal itself, like what kind of signal are you getting uh, from any electronic recording. You should see that, and then Deepak can tell it's have extensive use in EEG.
Yeah. So
Story wise.
So we can take this as an example, but in place of audio, we can also use the neural signals that we get. So this will be a like intuitive example because we don't have availability of each device. So how we can collect data and process in real time, those things we can see. But also we have some toy data sets which we will discuss in the later classes. Once we get to know if we can do Fourier transform on this, and once we are comfortable with doing some operations on this signal, uh, we can start using toy data sets and analyzing it. So yeah.
Okay. Will you cover discrete Fourier transform in next class, or it will be like fast Fourier transform, discrete Fourier transform? Those kind
Okay, fast Fourier transform comes later, like that's what the computer does, but I will not right now deal with it. I'll just show the like I'll try to make the Fourier transform more intuitive by showing the
Okay.
proof and how we can take from signal, and we can also see like if I filter particular part of the frequency from the signal and recreate and see how the voice changes or how a music can change if you remove that frequency, which is similar to what Atharva was saying, that we try to remove line noise, that's the 15 hertz noise, and see how it works. So yeah. So as you increase your pitch, right, this the oscillations will increase here. So that also you can see. So I'll share this code with you. You can explore how a waveform changes based on at what frequency you speak, and you'll get a more